here. So in one of the modules, in module 1, you will see this periodic table. No, why it's not clear very well. So this is a periodic table. It's kind of blurry, but this is a periodic table on Canvas. So you don't have to go to Google. You can just print this one out. It's it's on your module 1 in Canvas. So let's just move quickly to this work. Yes, it's necessary to print this one. Okay, so before we go to all right, so I asked that question in the discussion, and almost everybody did very well in the discussion. So you guys have read in empirical and molecular formulas. So of course we all know what the definition is. Empirical formula, by the way, is actually determined experimentally. That name empirical just makes experimentally determined. So there is a lab we do, I believe in General Chemistry 1 or Intro Chemistry, that determines the empirical formula of magnesium oxide. So basically, that lab basically helps us to know how to determine empirical formula experimentally. So we're just going to quickly look at some problems quickly before we move on. So just to have an idea, example of empirical formula. All right, so this first one here, it says write the empirical formula of glucose, and that is CH2O, because of course we all know that empirical formula, you just take the lowest whole number ratio for the empirical formula. All right, so if some things, I mean some substance, some compounds, the empirical formula is the same thing as their molecular formula. For example, carbon dioxide, the empirical formula is CO2, and its molecular formula is also CO2. All right, look at this, practice 1. Tetracarbon dioxide is an unstable oxide of carbon with the following molecular structure. So this is molecular structure. We're going to look at structures as well in this chapter 2 before we finish. We're going to look at the best way to represent our structures in chemistry, especially organic compounds. So the question says, what are the molecular empirical formula of this substance here? So basically, we want to see which of them is both empirical and molecular formula. So if we look at this cannot be it, A cannot be it, B cannot be it. So if we look at C cannot be it. If we look at D, so this and also E, D seems to be the only one that are both the empirical and molecular formula, because the lowest whole number ratio of C4O2 is C2O, right? If you divide everything out by 2, that will be C2O. So empirical is the lowest form of the molecular. And we can basically determine the molecular formula of a substance if we know the empirical formula. However, we cannot determine the empirical formula from the molecular formula. We have to know the formula. For us to determine the molecular formula from the empirical formula, we have to know the molecular mass that we are working with, the molecular mass of the molecular formula. Then we can determine the molecular formula from the empirical formula. That will be a discussion for chapter 3. In order for us to determine empirical formula from molecular formula, we have to have the lowest whole number ratio. We have to have what we call a small integer that we have to divide it through, divide the molecular formula through to be able to determine the empirical formula. That lowest whole number, the small integer, will be discussed in chapter 3. All right, so that is the example on empirical and molecular formulas. So basically, we all know that empirical formula is the lowest whole number ratio, and molecular formula is a real formula. So that is why you could have, you could have 2 or 3 empirical formula that are the same empirical formula for about two or three different molecular compounds. That's just because empirical formula is the lowest whole number ratio. Is the lowest whole number ratio. It's not a real formula, but it's the lowest whole number ratio. We are going to see that some ionic compounds, their empirical formula is the same thing as their molecular formula. They don't have lowest whole number ratio. When we talk about lowest whole number ratio, we're typically referring to molecular compounds or covalent compounds. All right, so we want to look at how to write chemical symbols for ions. So in this question, you are going to need your periodic table handy. So if you have your periodic table, you can have that handy to be able to see. And there's a periodic table here that I can show us right now. All right, so this is a periodic table in your book, and also this is similar to the one that is on Canvas. So basically, we know that, kind of making this bigger. All right, so we know that each of these columns are the groups, and the horizontal rows are the periods. So we're going to learn in chapter 5 that this number here, they are the periods, but they also represent something. So we're going to learn about that in chapter 5. For now, we just want to know how to use our periodic table to determine charges. Now, using the periodic table to determine the charges, it is very, very important for us to know how to do that, because once we get to chapter 3 and we start doing calculations involving reactions, you got to know how to be able to write chemical formulas, to balance chemical equations, write the formulas, and to balance chemical equations. For you to balance chemical equations, you have to know the charges, especially for ionic compounds. So the A here, I explained last week that the A's here, those are the representative elements, and the B's are the transition element. Okay, now they kind of like like a staircase here. This is separating the non-metals from the metals. So all of this in like the light yellow are the metals. This one, like the light green, something like this, is the non-metals, and the purple ones are what we call the metalloids. The metalloids, they basically have some characteristics of metals and some characteristics of non-metal. They're just in between. They have a little bit of non-metallic characteristics. They also have a little bit of metallic characteristics. So that is why these metalloids, they're typically used as semiconductors, because of course we know metals are very good conductors of electricity. Now, metalloids, those ones that are in between metals and non-metals, they could also be used as conductors. We call them semiconductors. They are not as powerful as metal, but they can also be used in place of metals, because some metals that are used for conducting could be expensive. Metalloids a lot of them can be used as semiconductors. A lot of them are used in photovoltaic cells, light emitting diodes. So we basically use them, because of the fact that they have some characteristics of metals. And we're going to look at metallic characteristics as we go on. All right, so this is just the periodic table. Now, in order for you to be able to determine the charges, there are some set in stone rule that we kind of use. It's like a shortcut way for us to determine charges. Now, group 1A, 2A, 3A, they basically assume their charges based on their group number. What that means is that lithium is in group 1. So lithium will have a charge of plus 1. So basically what that means is that when lithium loses its outermost electron, it's going to become lithium ion. Now, before I go to explain about charges, I want to talk about what this group number means again. Of course, we know it's a group number. Not only does it mean it's a group number, it is like, that number goes for all of the elements under it. So all of the elements in group 1A, they have similar characteristics because they belong to group 1A. Now, the reason why they have similar characteristics is because on their outermost energy level, we only have one electron. So I know many of you are kind of familiar with the Bohr model of representing atoms from your high school or wherever you've learned chemistry or science a little bit. So I want to draw the Bohr model of lithium. We're going to do all of this in chapter 5 when we get to electronic structure of atoms. So this is just to explain what the group number means. So I'm drawing the Bohr model. Bohr just is a scientist that came up with this. It's Bohr. This is a scientist that came up with the idea of drawing these little circles. and basically those just represent where the electrons are located around the nucleus. So this is a Bohr model of the atom. And then basically we have, let's just look at lithium. Let's look at lithium first. All right, now this is lithium. Lithium is in group A. So lithium, the number of proton in lithium is 3. So lithium has 3 protons. And how do I know? Remember, proton represents the atomic number. Proton represent atomic number. So the atomic number of lithium is 3. So that means the number of proton in lithium is 3. So if I want to put those 3 electrons on this Bohr model, so let me just put electron 1 here. This is electron 2 here. And by the way, we are looking at lithium as a neutral atom at this point. We're not looking at it as an ion. So lithium as a neutral atom, it has 3 protons and 3 electrons. When it becomes an ion, then the electrons will change. Remember, I explained that protons basically are the ones that identifies an atom. They basically identify an atom because they help us to know what is the atomic number. Okay, so protons identify atom. So lithium has 3 electrons. So we put 2 on the lowest, the innermost, the inner core shell. This is the one that is closer to the nucleus. Inside the nucleus, we have 3 protons. Okay, so around the nucleus, we're going to have 3 electrons. But all those 3 cannot just go on the first level. Okay, the first level can only hold 2 maximum. So once we put those 2 there, the next one, the last one we have, which is 1, we put the last one here. Okay, so what that means is that lithium has 1 electron on its outermost energy level, on its outermost shell. Okay, I mean, and I know you guys might think of it as shell. We call it shell, but it's typically the energy level. So basically, what that means is that this outermost energy level is the group numbers. The number of electrons on the outermost energy level represent the group number of all of these elements. So let's just discuss the representative elements for a moment, because it's easy to understand this thing looking at the representative element first before we start looking at transition elements. Okay, so lithium is in group 1A. It is in group 1A because there's just 1 electron on its outermost energy level, the last shell. Okay, of course, there are still some, you're going to chapter 5 that there's still some levels that is not been shown because electrons is not getting up to that. We're going to talk about that in chapter 5. For now, let's just keep it simple and just look at the outermost energy level, which is the last shell. Lithium is in group 1 because only 1 electron is in its outermost energy level. If you draw the Bohr model for all of these elements in group 1A, all of them have just 1 electron on their outermost energy level. So let me draw quickly for sodium. So let's just quickly draw for sodium so you can know why we came up with the group number. Sodium has 11 proton, right? So remember I said whenever you come, make sure you bring your periodic table so everything can make sense. And 11 electron. Neutral sodium has 11 proton, 11 electron. Neutron it's there. It's going to be 11 neutron. Depending on the isotope. Yes, that is why. Yes, that is why hydrogen is in that group. Now let us try to put all these 11 electrons on this shell. The first shell can only hold 2 electrons. Remember, the 11 proton is in here. Also, the 11 neutron is there. By the way, neutrons and proton, we're not going to be talking about that again till general chemistry 2. So this is electrons. 2 electrons. So we've used 2 out of our 11. We have 9 left. So the second one and on can only hold 8. So I will put 8 here. Once we put 8, that's it. We go to the next one. When we get to chapter 5, you will learn about how to write electronic configurations, and you will see that we don't normally do it this way anymore. We have a better way of writing electronic configurations. Now, we've used 10 electrons out of our 11 electrons. The last electrons goes here. The last electron goes here, which means that the outermost energy level of sodium has only 1 electron. That is why sodium is in group 1A. That is why sodium is in group 1A. Let us look at chlorine for a second. I'm going to erase this. Let's just look at chlorine for a second. Now, chlorine has 17 protons and 17 electrons. Your periodic table should be in front of you. You should be looking at it to be verifying what I'm saying. So let us draw the Bohr model for chlorine. And we know why chlorine is in group 7. Okay, this is 17. Let's just start putting it and see how, and see if that 3 is enough. All those E are electrons. So we've put 10 already. So we have 7 left. All right, so we put our 7. Chlorine is in group 7, right? Because it has 7 electrons on its outermost energy level. So in summary, all of those group numbers represent the, no, 7 is not the charge. We're going to get to the charge in a minute. All those 7 electrons represent the outermost energy level. Now let's get to charges, because that is where I'm actually going with all this. Charges is where, so I'm going to clear this board right now. All right, so now let's get to charges. Let us start with, well, let me start with lithium. And then I will go on to neon. Then I'll go on to neon. Then, all right, then I'll go on to chlorine. Let's see how we find charges from our periodic table. I'm assuming your periodic table is in front of you. So basically, to find charges, every atom on the periodic table, exactly, every atom on the periodic table, they tend to want to obey, I mean, to have a full octet. That is, did you see those outermost energy level I was showing you? They all want to have 8, because when they don't have up to 8, they are unstable. Why? Because they want to obey a rule that we call octet rule. Octet rule just means they want to have 8 electrons in their outermost energy level, because 8 is more stable. So 8 is what makes them stable. So if you have 1, you are not stable. You have 2, you are not stable. 3, you are not stable. 4, 5, 6, 7, you are not stable. Until you have 8, then you will be stable. So the only elements on the periodic table that have 8 are the noble gases. The noble gases are right there on group 8. You know why they're in group 8? Because they have 8 electrons on their outermost energy level. So they are stable. That is why noble gases typically don't form compounds, except in rare cases. They typically don't form compounds because they already have 8. The very first level is stable at 2 through right. From 1 through 7 is not stable. Only group 8 is stable, because group 8 is the only one that are, they basically obeying the octet rule. So what we are saying essentially is that all of the elements on the periodic table, they want to obey the octet rule. They basically want to be stable. I mean, everybody wants to be stable. So in the quest for trying to be stable, they typically form bonds. The reason why bond formation happens, whether it be ionic bond or covalent bond, is because all the elements are not stable except the noble gases. When they form a bond with somebody else, then they become stable. That person will supply what they need. That other person could be a metal and non-metal. It will be another element. So we're going to get to that in a minute. Now, for them to form a bond, they have to basically form their charges. Form the ions first. So here, what we are looking at here, we want to look at formation of ions. So let's just look at their ions. So what ions will lithium form, what ions with neon form, and what ion with chlorine form. This right here is neutral. We are going to see that the noble gases, they are neutral. So it's just neutral. They don't form anything, it's just neutral. So lithium will form lithium plus. That is the ion that lithium will form. You know why it will form lithium plus? Did you see the Bohr model for lithium, right, that I just showed us? Lithium has 1 electron on its atom's energy level. Therefore, in order for lithium to be stable, to obey the octet rule, it would rather give out that 1 electron. So metals in group 1, 2, 3, again, metals in group 1, 2, 3, they typically give out their electrons to become positively charged. Group 4, sometimes they share. So we leave group 4 alone, okay? Leave group 4 alone. You're going to see group 4 has things like carbon, that is the basis of organic chemistry. So we leave group 4 alone, then we go to group 5, 6, 7. So let me just kind of put a summary here. Group 1, 2, 3, metals. So what I've just written is this. Group 1, 2, 3 metals, they lose electrons on their atom's energy level to form their ion, So when lithium loses that last electron on its atom's energy level, it becomes lithium plus. The reason why, you may be wondering, why is it that when something loses, it becomes plus? Well, they are losing what is negative. So let me just kind of put it in context, in mathematical context. So basically, lithium basically has 3 electrons. And then when it loses 1, it's going to have 2 electrons left. That is why it is plus. The reason why it is plus is because electron is negatively charged. So when you lose electron, you are losing something negative, you become more positive. When you gain electron, you are gaining something negative to yourself, you become more negative. So lithium will form lithium plus. Okay? And then again, metals in group 1, 2, 3 lose electrons on their atom's level to form ion. So whenever you have your periodic table, it gives you a roadmap on where you are going. So every element on the periodic table, wherever they are, gives you a lot of information about them. A lot of information. Lithium is in group 1. Is the charge that it will form will be +1. So lithium will form +1 charge. Because all metals in group 1, 2, 3, they lose electrons to form ion. Same thing with sodium, same thing with potassium. Okay, for example, if we go to group 2, for example, let's just give an example of something in group 2. Calcium, for example. Calcium is right here in group 2. It will lose its atom's 2 electrons. If you draw that Bohr model for calcium, you see that it has 2 electrons to form calcium 2+. Okay, to form calcium 2+. So again, groups 1, 2, 3 metals lose electrons to form ion. Okay, now neon is stable, so it does not form a charge. Neon is not trying to obey the octet rule. It already has 8. If you already have 8, you are considered stable. Then you are already stable. So let's just go on to chlorine. Now that will just bring me to give a kind of general summary here. So groups 5, 6, 7 non-metals gain electrons to form electrons to form ions. So group 5, 6, 7 non-metals gain electrons to form ions. Now chlorine is right there in group 7. Okay, How we know how many electrons chlorine will gain is to just subtract 8 minus 7 is 1. So chlorine only need 1 electron to obey the octet rule. Now, because electrons are negative, when chlorine gains that electron to itself, it becomes Cl minus. So chlorine forms a -1 charge. Not only chlorine, did you see all those elements on group 7? All of them form a -1 charge. So whenever you are working with any of these elements, you don't need to memorize anything. You just need to have your periodic table in front of you. 5, 6, 7 will gain electrons to form iron. Let me just give more examples. Another example here is oxygen. Oxygen gain 2 electrons. Why will it gain 2 electrons? Is in group 6, right? Oxygen that we breathe in is in group 6, and its ion that will form will be O2 minus. We call this the oxide ion. This is a chloride ion. And this is a calcium ion. The non-metals, when you name them, okay, somebody asked, what about carbon? Like I said, carbon is in the middle. Carbon typically form covalent compounds. Covalent compounds formed by sharing electrons, okay? So carbon typically share electrons. It does not, it basically share electrons. That is why carbon is used in as organic compounds. And then another one I want to give is nitrogen. Nitrogen is right there in group 5. So what will be the charge for nitrogen, for nitrogen ion? When nitrogen gain, of course, we know that nitrogen is a non-metal, is going to gain. Yes, exactly. It will be 3 minus. So the charge for nitrogen, when it gains that electron, it will be 3 minus. Now, when it comes to the naming, this is lithium, but its name is lithium. But when it becomes an ion, it becomes lithium ion. See, all those metals, when they become ion, we give them their name as if it's their name. We just add ion. So this is lithium ion. Lithium ion. This is calcium ion. This is just neon. Then when it is just neon. Now, oxygen gains 2 electrons to become oxide ion. So basically, it's called oxide because it's non-metal. We drop the last 3 syllables and then we just change it to IDE. So we're going to talk about all this when we start doing naming now. Chlorine become chloride ion. Nitrogen become nitride ion. So this is basically called chloride ion. So that is why we call NaCl sodium chloride. And this one is called nitride. So you can see that non-metals, we drop their last syllable, 3 syllables, we change it to IDE, and metals, we just leave it alone. So for example, this is lithium ion, this is calcium ion. So the knowledge of how to determine ions, and charges is so important if I'm spending time on it. It is important for the rest of this course. It is very, very important. We use the periodic table till the end of this course. We don't need to memorize anything. The only thing you may need to memorize are the polyatomic ions. That is not directly on the periodic table, but for the monoatomic. So by the way, these are called monoatomic ions. Let me find where to write them. So this is called monoatomic ion. So these are called monoatomic. Somebody asked, is that why H2O is hydrogen dioxide and not yes. Now, actually, H2O is hydrogen oxide, but there are some compounds that we've given them a name. Now, water is chemical name is typically dihydrogen oxide, but nobody calls water that. We all call water, right? So H2O is actually dihydrogen oxide. Now, because we call it that name because it is it's a covalent compound, we name it by using prefixes: mono, di, tri, tetra, penta, all the way down to deca, 10. Okay, so yeah, so water is dihydrogen oxide, but we don't call it dihydrogen oxide. We just call it water. So it's okay to call it water. Yeah. Now let's just kind of go back to the work. The polyatomic ion, it's not that difficult to memorize. It's not that difficult to memorize once you get used to it. So based off of what we just learned right now, we're just going to kind of do some practice. So we've done, I think we've done most of the practice for the iron. We just need to start doing how to name compounds, because how to name compounds is a whole different one. All right, so let's just look at this practice 2 real quick because of time. So the question says, how many protons, neutrons, and electrons does 79, with a mass number, selenium 2 minus has? Okay, so this is an ion of selenium. And by the way, what group is selenium? Very good. It's in group 6A. Very, very good. It's in group 6A. So now let's just quickly do this one. And then you will see why we are doing this. All right, so what is the number of protons for selenium? Remember, number of proton is the same thing as the atomic number. Okay, good. It's 34. And the number of neutron, we are given the mass number in this question. So remember, the neutron will be mass number 79 minus 34. So just go ahead and do that quickly. 79 minus 34. Exactly, 45. Now, to find the electrons, remember that if this were to be a neutral selenium, then the proton will be equal to the electrons. But because this is an ion, is an anion, and by the way, if it's negative, it's anion. If it's positive, it's cation. That was the question I asked in the discussion. Positive ions are called cations. Negative ions are called anions. All right, so if it's an anion and it has 2 minus, that means we add 2 electrons to the proton. So the electron will be 36. Yes, it's correct. It will be 36. If it were to be a positive one, for example, if it were to be lithium that we just did just now, it were to be lithium plus, the proton for lithium is lithium has 3 protons. Lithium ion has 3 protons, but it has 2 electrons because it has lost 1 electrons. So whenever you see negative, just add that number of the ion to the proton to get your electrons. Whenever you see positive, you take away. Positive just means it has lost. Remember I said, when you lose an electron, you are losing something negative, you become more positive. Okay, so now let's just kind of move on to naming, because we really need to know how to name. Yeah, I think, let me see if we... All right, so predict what charges you expect for aluminum. So aluminum is the metal in group 3. So basically, the charge there is 3 plus. And fluorine is right here in group 7. Fluorine is just like is in the group of chlorine, so it's minus. So the charge for the most stable ion of fluorine is -1. The charge for the most stable ion of aluminum is 3 plus. Aluminum is right there in group 3. Okay, so remember I said metals in group 1, 2, 3. Okay, now which of compounds would you expect to be ionic? So by the way, we have 2 types of compounds. Remember, we have both ionic compounds and molecular compounds. Okay, I'm going to go back to the other file, which is the lecture portion, so we can quickly talk about this before we round up this chapter. As far as the naming and everything, and for you guys to know what table that you actually need to. So let me go down this way. Okay, so we have talked about all of these ions. These are the common cations. Okay, and before we go on to start doing naming, I'm going to give some rules and also some exceptions to the rules. All right, so these are the common cations that we well, before we go there, Um, yeah, I think we talked about this. Okay, so we know that we have the transition metals are different because they have the d orbitals. It's because of the presence of the d orbital. The d orbital is at a higher energy and it can hold 10 electrons. D orbitals can hold 10 electrons. So basically, it's because they have the d orbital. The d orbital is why they are kind of different in the way they behave. The transition elements. The d orbital can hold more than 8. Okay, how do we know the charge for them? We are going to talk about that when we get to ionic compound. I just want to touch on this one quickly before we get to what I just showed us now. So to know the charge for transition elements, it is just very, very simple. If something is not representative, it will be transition. And to know charge, you just have to know the charge of a non-metal. Like I said, we are going to do that. So quickly, before we do that, I think we've talked about this. So real quick, we have two types of compounds. We have ionic compounds and we have molecular compounds. And of course, we have metallic bonds and all those things. But in the context of this chapter, we talk about ionic bonds, covalent bonds. Ionic bonds is between metal and non-metal. Covalent bond is between two or more non-metals. Okay, ionic bonds, whenever they form, they are typically stronger than covalent bonds because they involve electrostatic interaction between a cation and an anion. All right. Now, talking about covalent compounds. Covalent compounds, we also call them molecular compounds. If you've seen the word molecular compounds, those are also covalent compounds. Okay? Ionic compounds are just called compounds. Covalent compounds, we call them molecular compounds. Now, all these ones that you are seeing here, they are example of covalent compounds. They are compounds that consist of two or more non-metals. Now, you would have heard the word binary before. Binary molecular compounds are those molecular compounds that typically have only two elements. Binary molecular compounds. So binary molecular compounds only have two elements represented in them. So basically, for example, something like this is just, for example, water is a binary molecular compound, and water is a covalent. It has covalent bonds and is a molecular compound because it has two nonmetals. H is nonmetal and O is nonmetal. By the way, on the periodic table, H is kind of categorized in group 1A, right? And that group 1A are metals, but H is not a metal. H is a non-metal. The reason why they put H in group 1A, even though H is not a metal, is because H, which is hydrogen, it fits in group 1A because its outermost energy level is just one. It has just one outermost energy level. Remember, they are arranging them based on the outermost energy level. They can't put H, which is hydrogen, they can't put it with a non-metal because it will no longer fit in. So that's why they put H. Some pretty put like a demarcation between H and lithium and the rest of them. So H, which is hydrogen, is a non-metal. It's not a metal, it's a non-metal. It behaves like a non-metal. So basically, water is a molecular compound because it has a covalent bond. We know covalent bond is typically involve sharing of electrons. Okay. Now we are going to spend more time on covalent compounds in this course than ionic compounds. We're going to look at their structures, writing the Lewis dot and all those things when we get to chapter 6 and above. So all of these are binary molecular compounds. Now you also have heard of ternary. I don't know if you've heard of it, but there's another one called a ternary molecular compound. I'll write that one out. Those ones have two or more. They have three or more compounds. For example, phosphoric acid or phosphorus acid is one of those, something like this. So you basically have three elements. All right. So now let's just look at example of molecular compounds and to see some rules that we have set for them. So molecular compounds are also called molecules. So if you hear the word molecules, it's from molecular compound. It's because they are just non-metals. If you hear the word compounds, it is ionic compound. An ionic compound has both metal and non-metal. So all of these 7 elements here, they basically exist in nature as diatoms. They don't exist by themselves. They exist as diatoms. What that means is that hydrogen, if you see hydrogen, if you want to isolate it, it's just going to be H2. They don't exist by themselves because they are highly reactive. They will rather exist in pair because by themselves, they are just extremely reactive. They cannot stay alone. They have to be in a pair. So all of these, they are called, they exist as diatoms in nature. And why is this important? It is extremely important because you are going to be writing molecular formulas. You are going to be writing equations for different reactions. Yes, they are based on binary. You're going to be writing equations. You have to remember that all 7 of these, they don't exist alone. H will not exist alone by itself. You won't see oxygen by itself. They exist together because they are highly reactive and they just can't exist alone. No, I mean, as far as the empirical formula, we don't have to reduce anything here. They exist alone. Now, empirical formula has to do with mainly with binary molecular compounds. So, with when you have 2 different elements, it's just one element existing together which is same element, but then they exist as diatoms. So when we use the word binary, we're basically we're talking about 2 different elements. This is just not 2 different, it's just diatoms. Okay, we have talked about this. Now, make sure you kind of look at all of this to see how structures, molecular compounds are represented. We use different structures for representing them. And then we've talked about cations, so I just want us to get to these ions. All right, so these are the ions. The ions that is just one element are called the monoatomic ions, and the ones that are a group of elements are called the polyatomic ions. Okay, so for positive charge ions, the cations, the only one in the context of this chapter, the only polyatomic ion that has a positive charge is this ammonium ion. Okay, is this ammonium ion, NH4 plus. It has a positive charge. So in a compound, it behaves like H plus, like Li plus, because it has just +1 there. Now, these are also the continuation of the monoatomic ions. Now, let's come to transition elements. I hope you have your periodic table in front of you. Transition elements, they have variable charges. That means, let me write it with the text so I can write it very well. Transition elements have variable charges. The reason why they have variable charges is we are going to learn that. I mean, one of the implications of their variable charges is because they are very colorful elements. If you've ever worked with transition elements, they are very colorful. And that's just because they can exist in different charges. For example, we could have ion 2, ion 3, we could have mercury 1, mercury 2. How then do we determine their charges? How then do we determine, for example, let me just give us a very popular one. FeO. FeO is an ionic compound. However, it has a transition element there. Okay, if you are told to name this, we're still going to talk a lot about naming, but let me just use it as an example. If you are told to name this, you can't just call this iron oxide. You got to determine what charge is ion using here. That is, which ion which ion, ION, of ion, IRON, is it using in this compound? Because ion can either be Fe2 plus or Fe3 plus. How we know is just to do a simple algebra. That algebra I'll just quickly show us here before we move on. If you are told to name this, again, you don't just call it iron oxide. You don't call it iron oxide because of number one reason. If you want to name anything, you first need to determine, well, is this ionic compound or molecular compound? For ionic compound, we name them using their charges. For molecular compound, we name them with their prefixes. We're still going to get to that. Now, because this is a metal and a non-metal, this obviously is an ionic compound. FeO is an ionic compound. So it's got to be named by its charges. Now, we don't just call it iron oxide. If this were to be sodium here, then I can call it sodium oxide. Whenever you are dealing with transition elements, if you want to name them, you have to know that almost all of them have variable charges. So which ion you are dealing with, you don't know. That is, which charge you don't know until you calculate it. The only 3 transition elements that have fixed charges are these. Let me just write it here: zinc, cadmium, and silver. Zinc has 2+ charge. Let me just write it on top here. Zinc has 2+ charge. Cadmium has 2+ charge. And silver has +1 charge. So did you see all these 3 transition elements? These are the only ones that don't have variable charges. We basically use, they have fixed charges. So these are their charges: zinc 2+, cadmium 2+, silver +. The rest of the transition elements, they have variable charges. In the context of what we are discussing, they have variable charges. So I will give us a lot of examples so you can understand what this is all about. Let's just look at FeO. FeO is an ionic compound. Why? How do I know? It has both metal, ion, and non-metal, oxygen. I can't just call this iron oxide because iron, Fe, happens to be a transition element. I know that transition elements, they present variable charges. They have different multiple charges. They could be one, they could be the other. As long as they are not zinc, cadmium, silver. If they are zinc, cadmium, silver, zinc will always have 2+, cadmium 2+, and silver +. All the other ones in the context of this, they have multiple charges. How I know is I basically do simple math. What is that simple math? I make ion the unknown. So this is what I do. I said ion, Fe, plus oxygen. Now, the charge of oxygen is -2. Everybody knows that oxygen has a fixed charge, okay? Remember, the only one that I don't have fixed charges are the transition elements. Oxygen has a fixed charge of -2, equals 0. This 0 just means that we know that all compounds should be neutral. Every compound should have a neutral charge except the polyatomics, ions, okay? So now doing this, completing this simple algebra, this simple math, I would just say Fe equals 2, which means that the charge that ion is using here is 2+. So this compound FeO is named iron 2 oxide. So let me write it here. It's named iron, and I'll put it in Roman numeral, 2 oxide. You guys can see it very well. So FeO is named iron 2 oxide. It's named iron 2 oxide. Why is that? Because Fe can present 2 different charges. It can be +2, it can be +3. How do I know which one is Fe is using in this? I have to look at the non-metal that is attached to it. Now, in all the compounds you will get, it will always have, for the ionic compounds, will always be normally metal and non-metal. And all the non-metals are the ones in 5, 6, 7. So the non-metals that we're going to be looking at will be the one in 5, 6, 7. Carbon, group 4, just leave that alone. It's typically organic chemistry, elements. Carbon is organic chemistry elements. So we talk about that when we talk about covalent compounds. For ionic compounds, all the non-metals you will get will be the ones in group 5, 6, 7. 5, 6, 7. Again, 5, 6, 7. Okay, so 5, 6, 7. So ion in this compound is using its +2 charge. So it's iron 2 oxide. It is iron 2 oxide. So that is why we have Fe2 plus here is iron 2. We also have Fe3 plus, which is iron 3. Example of iron 3 will be Fe2O3. So I mean, you can calculate that on your own. You will see that Fe2O3. Let me write it down. So you can do that as a homework to determine how you determine which charge ion is using here. This is Fe2O3. If we do that simple math, that it will be 2Fe plus, minus 6 equals 0. Does that make sense? It will be 2Fe minus 6 equals 0. So let me just do it quickly. Minus 6 equals 0. So that means that Fe equals 3. So in this example here, Fe2O3, ion is using its plus 3 charge. So basically it's iron 3 oxide. So this is iron 3 oxide. So I hope that makes sense. So that's basically iron 3 oxide. So back to what we are doing here. Now, all of the transition elements except zinc, cadmium, and silver, they basically, we use Roman numeral when we name them. To the Roman numeral would tell us which charge is the ion, is that transition element using. So the one we did here is iron 2 oxide, we have iron 3 oxide, and then, by the way, this is mercury 2, this is mercury 1, this is mercury 1. So I will give us some examples as we go along. So these are all monoatomic ions. So now these are the these are the polyatomic ions that you will need to memorize for the exam. And again, you don't need to memorize it if you follow the pattern that is given in the book. You don't need to memorize this. So these are the ones, the polyatomic ion that we really need to know. Okay, these are the ones that we need to know. So yeah, this is the polyatomic ion. The only polyatomic ion in the context of this chapter that is positively charged is ammonium ion. So polyatomic ion is a group of non-metals typically that have a that have a charge. Okay, that charge goes for the whole thing. That 2 minus charge goes for everything. When we get to chapter 8, chapter 9, we will learn how to draw the structure of this, and you understand why this charge goes for the whole compound. So we've talked about ionic compounds. We've talked about the fact that, well, we all know that ionic compound is made up of metal and non-metal. Now, the mechanism involved in the formation of ionic compound is simple. Electrons get transferred from the metals to the non-metal. Because metals, they typically have lesser amounts of electrons on their outermost energy level. Okay, now they are trying to obey, to assume octet. That is, they basically want to have 8. In order for them to have 8, they would rather lose than gain. So metals are known to lose electrons. As a matter of fact, the strength of a metal, how easy it is to lose electrons. When we get to activity series in chapter 4, you will see how this plays a role in things like corrosion that we see every day. So metals are important in the sense that they are able to lose their electrons. When they lose their electrons, non-metals are sitting there waiting for someone to give them electrons. For example, chlorine is right there in group 7. It needs only 1 to have 8 electrons, right? So sodium is a good partner for chlorine because sodium has 1 to give out. Chlorine needs 1. So sodium transfers out 1 to chlorine and it becomes a compound. Now, what happened in the mechanistic view is this. Well, we know that sodium has 11 protons, 11 electrons, that is neutral sodium. When it loses 1 electron, it becomes sodium ion. That sodium ion, we have 10 electrons, right? Now, remember we talked about that. That is why it becomes Na plus because it lost 1 electron. Chlorine, on the other hand, has 17 protons, 17 electrons. Neutral chlorine has 17 protons, 17 electrons. When chlorine gains electron, it basically becomes chloride ion, so it becomes Cl minus. So when Na plus and Cl minus comes together, they form a compound called ionic compound, called sodium chloride, the table salt we use every day. So that's sodium chloride. Now, this little image you see here is the crystal lattice of sodium, and basically the little purple balls are the sodium ions, and the green ones are the chloride ions. The reason why the sodium ions seem smaller is because when something loses electrons to become a cation, it becomes smaller. Cations are small, are typically they have a smaller size than their parent atom. We will discuss this in chapter 7. I don't want to overwhelm you with why this is small, why this is big. Just know that this is sodium chloride and is a crystal lattice. I mean, this is a crystal lattice of sodium chloride. Sodium chloride is an extremely strong compound because every ionic compound is very strong. That is why when you try to melt salt, and you try, I don't know if you've done it in the lab before, when you try to melt salt and melt sugar, sugar melts quicker or faster than salt because sugar, for example, glucose, has covalent compounds, and salt is ionic compounds. So anything that has ionic compounds, ionic compound inside it, it takes a longer, it has a very high melting point. That's why the melting point of salt is close to 800. It's very high. Whereas if it's a covalent compound, the melting point is very low. Okay, so that's ionic compounds. Now, this is just how we write formulas. Now, this crisscross method is kind of the way the easy way for us to basically learn how to write formulas. So a very good example is magnesium ion and nitrite ion that I gave us to do. So I'm just we're gonna do some more examples right now. So from now on, we're going to start doing examples on how to write and name compounds for ionic compounds, acids, molecular compounds, and organic compounds. For organic compounds, we're not going too deep into it. We just stop at alkanes, the hydrocarbons. All right, so we're going to start off with inorganic nomenclature. Whenever you see the word inorganic, it's just another word for ionic compounds. Inorganic just means it contains metal and non-metal. Okay, so inorganic just means it contains, this word inorganic, it just means it contains metal and non-metal. When you see organic compounds, the typical example are the hydrocarbons that contains H and C, for the hydrocarbons. All right, so when we name inorganic compounds, the word nomenclature is just a big word for naming. Whenever you see nomenclature, it's just naming. All right, so we want to look at how do we name ionic compounds real quick. I've given us a very good summary on how to name transition elements. Now, let's just see if now we have a polyatomic. So remember that ionic compounds consist of ionic compounds consist of metals plus non-metals. Ionic compounds consist of metals plus non-metals. So that non-metal could either be a monoatomic ion in the case of sodium chloride. So let me just give us a good example here. All right, let me look for a very easy example. Sulfate. Okay, I'll use calcium oxide. So this is CaO. So this is calcium oxide. So the name of this is calcium oxide. So this is calcium oxide. Okay. Why do I call it calcium oxide? Well, I know this is CaO. Ca is calcium. O is oxygen. When they come together, they form ionic compound, right? We know that it's ionic compound because it's calcium and oxygen. In this chapter, you only need to determine, to know, you will not be asked to describe the mechanism and all those things. We do that later on. So basically, just for you to identify ionic compounds and molecular compounds, so you can know how to name them. That's what this chapter 2 is all about. You know, the periodic table, to know how to get your charges, how to know how to name all these compounds. So you can go on to stoichiometry in chapter 3. So this is calcium oxide. Now, in this case, oxide is the anion combining with calcium, and then we call it calcium oxide. So what if calcium is combining with a polyatomic ion? For example, let me just give us one example here. When I'm done writing, you will see what I'm writing. All right. Okay, this is calcium nitrite. This is calcium nitrite. Now, did you see how I wrote that? I'm just going to kind of show us how we get this. So I'm going to use the other one to write. So let me just kind of write it here. I will actually open a bigger place for me to show this. All right, I'm just going to clear this. Okay, so I give example of calcium nitrite. We know that calcium has +2 charge, right? Is radium group 2, and nitrite is a polyatomic ion that has -1 charge. So when we want to write the formula for this, if we use a crisscross method, we just kind of bring this here, we just kind of bring that there, right? And then we write Ca. The reason why we put a parenthesis whenever we are dealing with a polyatomic ion in a compound is just to keep it neat and not to be confusing. Because polyatomic, they are together, right? They're just group of nonmetals together with one charge. So we put 2 here. That 2 is from calcium. We put 2 here. So we use that crisscross method to be able to get the charge for this. The crisscross method is just basically telling us that in order for this compound to be neutral, so this compound has a neutral 0 charge. Remember, in the beginning, I will explain why we do this. In the beginning, we have calcium ion and nitrite ion. Calcium ion has +2, nitrite has -1 charge, right? If you want to form a compound, remember every element in the periodic table, they basically form a compound to obey the octet rule. And then the octet rule says that they must all have 8 on the outermost energy level. They must, you must have 8. So the reason why they form a compound is because a compound will have 0 charge. Any compound should have 0 charge except the polyatomic ions. The polyatomic ions, they are, even though they are compound, but they are unstable. That is why they form a compound. Anything that forms a compound is unstable. Okay, so but a compound, the driving force of the formation of a compound is to have is to be neutral, is to have 0 charge. Okay, so so if you are told that what would be write the formula for the compound that exists between calcium ion and nitrite ion. Calcium ion has 2 plus charge, NO2 has -1 charge. In order for us to offset that, we got to bring the 2 here, and we will bring this here. So when we do that, then we can have a 0 charge. Does that make sense? We have a 0 charge. So another way to look at it is if we have 2 here, and then we have 1 here. So what do we need to multiply this with to make 2 is 1? What do we need to multiply 1 with to make 2 is 2? So that's why we brought the 2. So basically, the 1 goes here and the 2 comes here. So this compound is called calcium nitrite. So this is calcium nitrite. This is called calcium nitrite. Okay, so same thing with the one I showed previously was a calcium oxide. That one basically has for the let me show that one so you can let me show that, and then you will see why we have that. So let me show that one. Let me write with this. All right, so if you are told to write the formula of the compound that exists between calcium ion and oxide ion, or write the formula between calcium and oxide. So basically, both of them have the same charge. So you don't need to do crisscross anything because +2 minus 2 equals 0. Remember, the driving force of formation of a compound is to have a 0 overall charge. So a compound should have a 0 overall charge. So the formula for calcium, the formula of the ionic compound that form between calcium and oxygen is CaO. This is calcium oxide. Did you see we didn't have to put any 2 here because oxygen already have 2 minus. So let me just give one more example of this. So another example of this is if you're able to write the name of, write the formula of the compound that exists between scandium 3 plus and nitride ion. These also have the same charge, so it will be scandium nitride. So it will be SCN typically. Now another, okay, I didn't say this question. Didn't calcium and nitrogen cancel out? No, let me give you, let me show that again. Now, this is calcium. Calcium is 2 plus. This is nitrogen. Nitrogen is right there, is 3 minus, right? It's in group 5. So when we do a little crisscross thing that we do, and I hope we all understand, I try to explain why we do that crisscross. So we have, so the 3 we go here, and the 2 we go here. So calcium is 2 plus, N is 3 minus. We have Ca3 and 2. So that's just how we write these formulas. So basically, you can say that all you need to know to write formulas is to know the charges. Just know the charges, and then you can write the formulas. For calcium oxide, it was the Ca2 plus, like I think I explained this one for the person asking that question. Just trying to write very well with this thing. So yeah, it's Ca2 plus for calcium oxide and O2 minus. So when we have that, it cancels out. So it's just calcium oxide. When you have the same charge, it is 0. It's electrically neutral, it's 0. When you have different charges is when you do your crisscross. When you have the same charge, it cancels out. These two now, they cannot cancel out. That is why we do the crisscross. That makes sense. The crisscross is to balance the charges, because what do we multiply 2 with? Now, the number that both of them, that is common to both of them, is 6, right? The lowest number will be 6. So what do I multiply 2 with to make 6 is 3. What do I multiply 3 with to make 6 is 2. So that is why we do the crisscross. Okay, so this is for calcium nitride. This is for calcium oxide. If it's the same charge, you just cross them. If it's not the same charge, to make it easy, you just do the crisscross. And I explain why we do the crisscross. Okay, so I think we can go back right now to what we are doing previously. All right, so we talked about the polyatomic ions that you need to, so that table for the polyatomic ion, you need to remember that one. So right now, we just want to, let me just go back here. I think where we have right now is, let me see. No, we get there. It's another one here. Okay, so we're gonna do naming, and okay, I think I've done that. Before we get to acid naming, acid and nomenclature, and also molecular compounds, let's just quickly do this, and then we go to molecular compounds naming and naming naming acid. Okay, so we've learned a lot today about naming ionic compounds. So I hope everybody got the idea of how we name ionic compounds. So remember, ionic compounds contains metal and non-metal and covalent compounds or molecular compounds contains all non-metals. Can you show that table? So which table is that? Is it the table of the polyatomic? I don't think that table will be in their other file. So let's answer this one first. Go back to the other file. Which of these compounds would you expect to be ionic? Obviously, looking at this is N2O. This is all non-metals. This is Na2O. This is metal, non-metals. So that will be ionic. And also this will be ionic. This is SF4. This is in all non-metals. So this is a binary molecular compound. This is not an ionic. Okay. So right now we want to look at how do we name molecular compounds. So when you get home, I mean, of course, you're already home. So just kind of write down the empirical formula for this. So try this based on what we've done today. Try this practice 2. Try this practice 2. So try this practice 2. Just write down the compound. For example, let me just kind of give us an example. This is Fe3 plus and CO2 minus. When you crisscross, the 2 minus will come to the Fe, the 3 plus will come here. So if you want to write that, you just click crisscross. That crisscross method is kind of, it's easier for a lot of people to understand. So because the 2 the 2 minus is going to go on that side. So that is why we put our 2 here. And then we put this in parentheses. Whenever you're dealing with polyatomic ionic compound, you want to make sure you put them in parentheses or it's just going to be confusing. And then that 3 plus will come here, making it a neutral compound. So it's just crisscross. This goes here, that goes there. So you can try the rest at home. Now let's look at how we name molecular compounds. Those are much easier to name than ionic compounds because you don't have to deal with the charges. When you're naming molecular compounds, that is the compounds that involve nonmetals, you don't, I mean, that is much very easier to name. All you need to remember is to remember your prefixes. So let me go back here. And instead of memorizing the polyatomic ions, just follow these patterns here. There's a pattern that is already given here. So it follows a pattern. So basically, the pattern is given by the period the polyatomic ion, the first element contains. So that pattern is what you basically need to follow so you don't have to memorize it. So let's just look at how we name molecular compounds. So we're looking at how we name binary molecular compounds. Binary molecular compounds. When you name molecular compounds, we use prefixes. The reason why we don't use charges is because molecular compounds, there's no transfer of charges. There's no transfer of electrons, essentially. Electrons are shared in between atoms to form a covalent compound. So in covalent compounds, electrons are shared. In ionic compounds, there's a complete transfer of electrons from the metals to the non-metals. So that is why we have to name and write ionic compounds using their charges, okay? So, and keep in mind that for the transition elements, we're using Roman numeral except for the zinc, cadmium, and silver, okay? So let's just look at this and then look at acid and then we conclude for today. On Wednesday, we do more practice and also we go to chapter 3 on Wednesday. If you have questions, you can always email or bring it. So to name binary, remember I said binary means it has 2 elements. Molecular compound, that is compounds that have covalent compounds. We use prefixes. So you got to remember all of these prefixes. See this table? You have to remember this table. On that study guide I put on Canva, there's a module called Test 1 module. You will see the study guide here. So I kind of put all of the tables you need to know, what will be given, what will not be given. So that is for you to just know exactly what, because it's not everything that will be on the exam. So you just need to focus on the important ones. Well, most of them will be, but not really everything. All right, so we have mono, di, tri, all the way to deca. So now let's just do an example. I think that's an example next year. Okay, so here is called carbon dioxide. This is carbon tetrachloride. This is dinitrogen pentoxide. This is carbon monoxide. Now, there are some elements. Let me just go here. There are some compounds, some molecular compounds that we typically have a common name that we call them. And therefore, we don't go by that, that name using prefixes. A very good example is water. A very good example is water. Water is H2O, right? Okay, so typically we should say that based on the prefix rule of naming, of naming molecular compounds, water should be dinitrogen oxide. Water should be dinitrogen oxide, but we don't call it this. I mean, nobody goes about calling it this. We call it water. So things like H2O, water, they have their common name. Another example of something that has a common name happen to be ammonia. Ammonia is a gas that has a very foul smell. Um, so this is ammonia. Well, the name should be nitrogen tetroxide, but we don't call it nitrogen tetroxide. So let me write it down. So this name should be nitrogen tetroxide. And you can see I kind of dropped that O and then it just use just one O here. Whenever we have just one element, we don't have to use mono. The mono prefix goes typically for the second element. Okay, so if it's just one, you don't have to put mono in front. We don't typically need that. We don't need to do that because we know if it's nitrogen, it's just one. Now, to name molecular compounds, the first non-metal will retain its name, and then the second one will end with the IDE. So now this nitrogen, sorry, trioxide. What am I writing here? So this is nitrogen trioxide, not tetroxide. Trioxide. So this is nitrogen trioxide. However, the name that we call this, the generic or the common name we call this is ammonia. So remember, I said some of them like water, we don't need to follow this rule to name them, but then this is typically called ammonia. Just like water is called water. We don't call water nitrogen oxide. Even in the lab, we call it water. Ammonia, we call it ammonia, even though it's nitrogen tetroxide. Nitrogen trioxide. So I'll just give us a few more examples of how we name molecular compounds. So how do we name something like this? Let me use the other right hand thing to do this. So how do we name something like this? So how do we name something like this? So you can type it, and I don't think I can unmute you guys. With this mode I'm using, I might not be able to unmute you guys. If you want to write the answer down, you can write it if you know what the answer would be. So again, this is a molecular compound, a binary molecular compound that has both two of the elements involved are nonmetals. To name them, we use prefixes, right? And then let me just show us how to write this. So the name of this will be tetraphosphorus decaoxide. I will show it now. So this is tetraphosphorus decaoxide. So this is tetraphosphorus decaoxide. Why is that? Now, remember that this is 4. We name molecular compounds using prefix, okay? Okay, somebody say they can't see. Okay, let me write it up here so you can see it better. Can you see it now? Oh, you still, okay, let me kind of clear this and use a fresh new board so it can be clearer. Okay, so the one I'm doing is actually this. The name of this, well, let me first write the formula for this. The formula for this is, well, I mean, the name is, well, the speed for O10. So the name will be tetraphosphorus decaoxide. So can we all see that? So this is tetraphosphorus decaoxide. Why do we call it that? This is a molecular compound. If you are told, okay, what would be the name of this compound? The very first thing you want to ask yourself, well, would this be, yes, would this be ionic or molecular? It is molecular. It is a binary molecular compound. And that's the one we are doing in this chapter, except for the acids. So this will be a binary molecular compound. So it's tetraphosphorus decaoxide. So we use prefixes only on molecular compounds. This tetra is because there's 4 here. Did you see that little table I showed us for the prefixes, mono all the way to deca? You want to memorize that table for the exam. 10 is deca. Okay, so let me just kind of give us another one now before we close today. S2 CO2. Okay, can we try to name this? S2CO2. Let me write it down. So somebody asks, why is H2O dinitrogen oxide when there is, oh, sorry, it's dihydrogen oxide. Did I put that? It's dihydrogen oxide. So H2O is dihydrogen oxide. It's dihydrogen oxide. So H2O is dihydrogen oxide. N2O is dinitrogen oxide. So this is for this last one we are doing because time has gone. All right, so this is disulfur, exactly. Disulfur dichloride. So this is disulfur dichloride. Yes, disulfur dichloride. That's how we name this. Disulfur dichloride. If it's just SCl2, it will be sulfur dichloride. So if it's just one here, if there's no two and above here, we don't need to put monosulfur. We just call it sulfur dichloride. So, but if it has like two, it's disulfur dichloride. Just like water is dihydrogen oxide. In periodic table, we have the names of the element. Yes, we have names of the elements in the periodic table. Does that answer your questions? So, any more question for today? So when we come back on Wednesday, because time has gone, we will look at acid nomenclature. Now that we all know how to name the ionic compound or the molecular compounds. All right, so can you rewrite that question? Said, can you rewrite that question? Oh, okay, you only have symbols. So yes, we only have symbols. Yes, we only have symbols. But then the names are in the back of your textbook. I can attach another one that has names. I'll attach another one that has names, but in your textbook, you have the names. If you have the text, every chemistry textbook have both the symbols and the names. For example, in the textbook, on the periodic table, they will just put the symbols, and there will be another page where they will write the names. But I will try to see if I will attach another periodic table that has names, so that you can not only, but that one, the names will be really small. No, yes, you're not allowed to use your textbook on the, yes, you're not allowed to. Okay, yes, the one with the names will be attached. Yes, I will attach the ones with the names. I will attach two, both the ones with the names and both the one with just the symbols. All right, any more questions for today? All right, so just make sure you review everything we did today. We kind of went fast today. Just try to review, because chapter 3 is pretty big. It's a lot of work. I mean, not a lot of work. It's easy, but it's just a lot of calculations. So we're going to continue from here on Wednesday, and we're just going to do acid nomenclature, and then we go on chapter 3. All right, so if you have any question, you can always ask. So I'll see you guys on Wednesday. Have a great day. Will you put it in the modules? Yes, I'll put it in the modules.